We're talking about the elimination reaction, specifically the E2. Let's talk about the mechanism first. This has been discussed already, but let's review. And like I said, if you can understand this mechanism really well, the E2, the E1, the SN1 and the SN2 and the SN1 we have already covered. And then we'll talk about the addition reactions. If you can understand the mechanism, the stereochemistry, the specific requirements and steps of each of these reactions, then you can apply that same knowledge to a lot of different reactions. For each one, you can apply that knowledge to a lot of different reactions. So let's review what happens in the E2 mechanism. In the presence of a strong base, an alkyl halide, and actually more generally we can call this any leaving group. LG, any good leaving group. And so what we need as the substrate is a carbon skeleton with at least 2 carbons, where 1 carbon has a leaving group attached and the adjacent carbon must have at least 1 hydrogen attached. And what happens is, in the presence of a strong base, this structure becomes an alkene. And the steps, if you remember, are the base abstracts a proton, the CH bond density moves between the 2 carbons, makes a pi bond, and the leaving group leaves with the electrons, so the CLG bond is broken heterolytically, and the LG leaves with the electrons. And the transition state will involve the base partially bonded to the hydrogen, where the BH bond has not yet formed completely, it's in the process of forming. The H is attached to the carbon simultaneously, so the H at this point is attached to the base and the carbon simultaneously. There's the sigma bond, and we make a dashed line for the newly pi bond that's being formed between the 2 carbons, and the LG bond is also an LG because the leaving group has not yet left, but this bond is being broken. And everything else just is carried along. And that is our transition state for the E2 mechanism. Now the reason I think it's better to learn the E2 first, when you're doing substitution, it's better to learn the SN2 before the E1, is this basically summarizes all the steps that happen in elimination. And we'll discuss what's different in E1, but let's finish talking about the E2 mechanism first. So that's our transition state. And to do the products, we know that there's a double bond formed between the 2 carbons. The leaving group has been lost from this group. And these are the 2 groups that remain attached. and that's our product, alkene, with the base attached to the hydrogen and the leaving group, usually a halogen, and these are our products. Now we'll talk about the stereochemistry of this reaction. But first, before we go to stereochemistry, let's review mechanism again. What's happening here is the base is attacking the H. At the same time, the CH bond is moving, the CH bond density, the electrons between the C and the H are moving between the two carbons. At the same time, the leaving group is leaving. All these three electron movements, the base donating the lone pair to the hydrogen and removing the hydrogen, the CH move electrons, these electrons moving between the two carbons, and the leaving group leaving. This happens all simultaneously. As a result, there is a certain geometry that's required for this reaction to happen. The E2 is stereospecific in that so we discussed the mechanism. Now we're talking about the stereochemistry of the E2 reaction, and we say that the E2 reaction is stereospecific. And what that means is that a certain stereochemistry is required, stereochemistry between the two groups that are leaving, that are being eliminated, is required, and each different stereoisomers give different stereospecific stereoisomers of the product. So for example, if we have a carbon attached to another carbon, and this is a hydrogen, and that's her leaving group. Let's call this a bromine. This bromine and this hydrogen, whichever hydrogen is being removed, and the leaving group must be in the same plane, but they can be in the same plane by being anti to each other or by being syn to each other. And what we want is we want them to be anti to each other. So the base can approach the hydrogen and the leaving group can leave. And if you look at a molecule, a molecular model, and we actually built this alkane or alkyl halide. So if this is our hydrogen of interest that's leaving, that's being eliminated, then this is when the molecule has a leaving group or a halogen attached to the adjacent carbon. This is one way for these two atoms to be in the same plane, and this is syn coplanar. So we by saying coplanar, we want these two atoms to be in the same plane, and there's two ways for them to be in the same plane. This right now, they're in the same plane, meaning if you slice this molecule with a plane, these both will be, the plane will intersect both of these. So this is syn coplanar, and this has to do with the eclipsed conformation of the molecule. And if we rotate this, turn this around the carbon-carbon bond, that's again that's another possibility for these two atoms to be in the same plane with each other. Again, they're in the same plane, but they're anti-coplanar. And this is the geometry that's required for an E2 reaction to happen. And it's important that we know this, because when we later talk about the specific reactions that need this requirement, for example, dehydrogenation, debromidation of an alkyl halide or dihalide, when we talk about dehydrohalogenation, when an H and X is removed, the H and the X must be anti-coplanar from each other. So let's see how we can do an example.